Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of a person who finds rest not in silence, but in stories that matter, in quiet revelations about the world and the remarkable people who shaped it. Either way, tonight's journey is especially for you. You have nothing to do but rest. Let your shoulders drop, your breathing slow, and your mind wander gently through corridors of time. Because tonight, we're traveling through centuries of brilliant minds, persistent spirits, and discoveries that changed everything. We're exploring the hidden and celebrated stories of women in science, from ancient physicians to modern Nobel laureates, from those who worked in shadow to those who blazed trails bright enough to light the way for generations. Before we begin this journey, if these gentle explorations help you unwind, if they give you a peaceful way to end your day or spark quiet curiosity as you drift toward sleep, consider liking this video and subscribing to the channel. It helps others discover these stories too, one restful night at a time. Now, let's begin our journey through time, through discovery, through the lives of women who looked at the universe and asked, why? And how? And refused to accept that those questions weren't meant for them. The story of women in science doesn't begin in laboratories with gleaming equipment or in universities with marble columns. It begins much further back. In times when the boundaries between healer and scientist, between observer and philosopher, were still being drawn. It begins in ancient civilizations where knowledge was passed through careful observation, where understanding the natural world was not just curiosity, but survival. And in those distant times, women were there, watching, learning, healing, and teaching. In ancient Egypt, around 2700 to 2500 BCE, there lived a woman whose name has survived across more than 4 millennia. Her name was Merit Putta, and on her tomb, carved into stone that would outlast empires, she is described as the chief physician. Think about that for a moment. In a time so ancient that it predates the pyramids at Giza, in a civilization that would become legendary for its advancement, a woman held one of the highest medical positions known to that society. We don't know the specifics of her work, which diseases she treated, which remedies she prescribed. The desert sands and the passage of time have taken those details. But we know she existed, that her role was important enough to be commemorated, that she stood as proof that women's contributions to medicine and science reach back to the very foundations of recorded history. Moving forward through time, we arrive in the city of Alexandria in the 4th and early 5th centuries CE, a place that was then the intellectual heart of the ancient world, home to the great library, a crossroads of knowledge from across the known world. Here lived Hypatia, a mathematician, astronomer, and philosopher whose brilliance drew students from across the Mediterranean. She was the daughter of Theon, himself a respected mathematician, and she not only learned from him, but eventually surpassed him, becoming head of the Platonist school at Alexandria. Imagine her in that ancient city, teaching geometry and astronomy, commenting on mathematical texts, building astrolabes to measure the positions of stars. She lived in a time when philosophy and science were intertwined, when studying the movements of celestial bodies was considered a path to understanding divine order. Her students wrote of her with reverence, describing not just her intellect but her dedication to teaching, her ability to explain complex mathematical concepts with clarity. She wrote commentaries on works that would become foundational to mathematics, on Diophantus's Arithmetica and Apollonius's Conics, though sadly, none of her own writings have survived intact. What we know of her work comes filtered through the words of her students and later historians. Her life ended in tragedy, killed by a mob in 415 CE during a period of religious and political upheaval. But her legacy endured, a reminder that women's minds have always reached for the stars, even when the world around them was far from ready to celebrate that reach. The centuries that followed saw the rise and fall of empires, the spread of new religions, the fragmentation and reformation of knowledge. In medieval Europe, as universities began to form in the late 11th century onward, women were systematically excluded from these new centers of learning. But knowledge, like water, finds its way through barriers. In convents across Europe, women found spaces where they could read, write, and study the natural world. Among these remarkable women was Hildegard of Bingen, a 12th century abbess whose mind encompassed music, theology, medicine, and natural history. She wrote extensively about the natural world, documenting plants and their medicinal properties, describing human anatomy and health in ways that drew on both observation and the medical knowledge of her time. Her books, such as Physica and Causae et Curae, contained detailed accounts of natural remedies, descriptions of illnesses, and treatments that reflected a careful attention to the workings of the human body. She lived in a world where science and spirituality were not separate, where understanding God's creation meant studying it carefully, cataloging its diversity, learning its patterns. Hildegard was far from alone. Across medieval Europe, in convents and in their own homes, countless women practiced medicine and herbalism, preserving knowledge through oral tradition and handwritten texts, healing their communities even as official recognition remained beyond reach. The Renaissance brought shifts in how knowledge was pursued and shared, but it did not bring equality. Yet, even in this era of supposed rebirth, women continued to contribute, often working in the margins, sometimes gaining recognition, more often laboring in obscurity. The 17th century brought us Margaret Cavendish, the Duchess of Newcastle, a woman who wrote extensively on natural philosophy, what we would now call physics. In 1667, she became one of the first women to attend a meeting of the Royal Society of London, though she was never made a member. In an age when most women writers used male pseudonyms to be taken seriously, Cavendish wrote under her own name, publishing works on atomic theory, on the nature of matter, on the workings of the natural world. Her contemporaries often dismissed her as eccentric, but she persisted, arguing that women had the same capacity for understanding the natural world as men, that exclusion from education was the barrier, not ability. She wrote in her work, The Blazing World, creating what might be considered one of the first works of science fiction, a story that blended imaginative speculation with philosophical inquiry. Her voice, speaking across centuries, reminds us that claiming space in science has always required not just intellect, but courage. The 18th century, the Age of Enlightenment, brought new opportunities for some women, though the path remained difficult. In the University of Bologna in Italy, Laura Bassi became, in 1732, the first woman in Europe to earn a doctorate in a scientific field. And, shortly after, the first woman to hold a professorship in physics at a university. She taught Newtonian physics, conducted experiments, and became a respected member of the Bologna Academy of Sciences. Her appointment was remarkable not just for breaking gender barriers, but for what it represented about the possibility of women contributing to scientific discourse at the highest levels. Yet, even Bassi's success came with limitations. She was not always allowed to teach publicly in the way her male colleagues could, and much of her work was conducted through private lectures and demonstrations. Still, she persisted, publishing papers on physics, corresponding with prominent scientists across Europe, making her mark on a field that would have preferred to keep her out. In France, Émilie du Châtelet, born in 1706, became one of the most important mathematicians and physicists of her era. She translated Isaac Newton's Principia Mathematica into French. But she did more than translate. She added her own commentary, her own insights, helping to make Newton's complex ideas accessible to a broader audience. She conducted experiments in physics, studied the nature of fire and heat, and made original contributions to the understanding of energy. She wrote Institutions de Physique, a textbook that explained the latest developments in physics, and she corresponded with the leading intellectuals of her time, including Voltaire, with whom she had a long relationship. Du Châtelet worked in an era that was beginning to see the value of empirical evidence and mathematical proof, and she contributed to that shift. She died young, at 42, from complications following childbirth. But her work endured, her translation of the Principia remaining the standard French translation for 2 centuries. Across the English Channel, Caroline Herschel was making her own contributions to astronomy. Born in Hanover in 1750, she came to England to assist her brother, William Herschel, in his astronomical observations. But Caroline was far more than an assistant. She became an accomplished astronomer in her own right, discovering 8 comets, including the periodic comet 35P Herschel-Rigollet. She was the first woman to discover a comet, the first woman in England to hold a government position when she was appointed as William's assistant by King George III, and the first woman to publish scientific findings under her own name in the Royal Society's publications. She catalogued nebulae, created detailed indexes of astronomical observations, and continued her work well into old age, receiving medals and honors from astronomical societies across Europe. Her life spanned nearly a century, from 1750 to 1848, and across those decades, she demonstrated that women could not only participate in science but excel in it, making discoveries that advanced human understanding of the cosmos. In France, Sophie Germain, born in 1776, taught herself mathematics by reading books from her father's library, studying late into the night by candlelight. During a time when women were not allowed to attend university lectures, she corresponded with leading mathematicians, initially using a male pseudonym to ensure her work would be taken seriously. She made significant contributions to number theory, and her work on the elasticity of materials was groundbreaking, earning her recognition from the French Academy of Sciences. When her true identity was revealed, some respected her work regardless, recognizing that genius is not bound by gender. But Germain never received a university position, never had the institutional support available to male mathematicians. She worked independently, driven by passion for mathematics, and her contributions, particularly in number theory and mathematical physics, remain important to this day. As we move into the 19th century, the barriers remained high, but the cracks in them were widening. Women began to demand not just the right to learn, but the right to be recognized as scientists, as physicians, as contributors to human knowledge. This was the century when women began to formally enter scientific fields in larger numbers, though always fighting against resistance, always having to be twice as good to receive half the recognition. In England, along the coastal cliffs of Dorset, a young woman named Mary Anning was making discoveries that would reshape our understanding of prehistoric life. Born in 1799 into a working-class family, Anning began collecting fossils as a child, a way to make money by selling them to tourists. But she developed an eye that went beyond commerce. She learned to recognize patterns, to carefully excavate specimens, to preserve them properly. In 1811, when she was just 12 years old, she discovered the first complete ichthyosaur skeleton, a marine reptile from the Jurassic period. Over the following decades, she would discover the first plesiosaur skeleton, the first pterosaur fossil found in Britain, and numerous other specimens that became crucial to the developing science of paleontology. Scientists from across Europe came to Dorset to buy her fossils, to consult with her about their finds. Yet, because she was a woman, and a working-class woman at that, she was rarely given credit in the scientific papers that were written about the fossils she discovered. The gentlemen scientists would purchase her finds, study them, publish papers, build careers, while Anning remained on the cliffs, her knowledge and expertise acknowledged informally, but rarely officially. It was only near the end of her life that she began to receive some recognition, being made an honorary member of the Geological Society of London, though women could not be full members. She died in 1847 at the age of 7 from breast cancer. But the fossils she found, displayed in museums around the world, stand as testimony to her skill, her knowledge, and her fundamental contributions to paleontology. Across the Atlantic, in America, Maria Mitchell was looking not down at the Earth, but up at the stars. Born in 1818 on Nantucket Island, she was encouraged in her interest in astronomy by her father, who was an amateur astronomer. In 1847, using a telescope mounted on the roof of their house, Mitchell discovered a comet, a find that brought her international recognition. She became the first woman elected to the American Academy of Arts and Sciences in 1848, and in 1850, she was one of the first 3 women accepted into the American Association for the Advancement of Science. In 1865, she became the first professor of astronomy at Vassar College, one of the new women's colleges that were being established in America. There, she taught generations of young women, encouraging them to pursue science, demonstrating through her own career that women could contribute to astronomy at the highest levels. She used her position to advocate for equal pay for women educators and for women's rights more broadly, understanding that her success in science was connected to larger questions of equality and opportunity. In England, Ada Lovelace was making intellectual leaps that were far ahead of her time. Born in 1815, the daughter of the poet Lord Byron, she was encouraged by her mother to study mathematics and science rather than poetry. In her 20s, she began working with Charles Babbage on his proposed analytical engine, a mechanical computer that was never built in Babbage's lifetime but represented a revolutionary concept. Lovelace wrote extensive notes on the analytical engine, and in those notes, she described something that Babbage himself hadn't fully conceptualized. She understood that such a machine could be programmed to perform not just mathematical calculations, but could manipulate symbols according to rules, that it could potentially create music, art, could be instructed to perform complex sequences of operations. Her notes included what is now recognized as the first computer algorithm, a sequence of operations intended to be carried out by a machine. For this, she is often called the world's first computer programmer. She died young, at 36, from uterine cancer, but her vision of what computing could be, written in the 1840s, predicted the digital revolution that would come more than a century later. In America, Elizabeth Blackwell was breaking barriers in medicine. Born in 1821 in England but raised in the United States, she applied to medical schools repeatedly, facing rejection after rejection, simply because she was a woman. Finally, Geneva Medical College in upstate New York accepted her application, possibly as a joke, thinking she wouldn't actually attend. She did attend, graduated first in her class in 1849, becoming the first woman in America to receive a medical degree. She went on to establish a medical school for women in both the United States and England, and she worked throughout her life to improve access to medical education for women and to improve health care for poor women and children. She understood that her own achievement was just the beginning, that for medicine to truly serve all people, women needed to be part of it, both as patients who were listened to and as physicians who could advocate from within the profession. As the 19th century progressed, more women began to enter chemistry, a field that was expanding rapidly with new discoveries and applications. Ellen Swallow Richards became the first American woman to earn a degree in chemistry in 1870, graduating from Vassar College and then becoming the first woman admitted to MIT, where she earned a second degree. She pioneered the field of sanitary engineering, studying water quality and the effects of pollution on public health. She was never given a formal faculty position at MIT, despite her extensive work there. But she continued her research, helping to establish standards for water purity that would save countless lives. She also helped found the field of home economics, not as a way to confine women to domestic roles, but as a way to apply scientific principles to everyday life, to improve nutrition and health in households across America. The turn of the 20th century brought us to one of the most famous scientists in history, a woman whose name has become synonymous with both scientific brilliance and the obstacles women faced in receiving recognition for their work. Marie Curie, born Maria Sklodowska in Warsaw in 1867, grew up in Poland under Russian rule, at a time when higher education for women was restricted. She worked as a governess to save money, then moved to Paris in 1891 to study at the Sorbonne. She earned degrees in physics and mathematics, working in conditions of poverty and, utterly dedicated to her studies. In 1894, she met Pierre Curie, a physicist whose interests aligned with her own. They married in 1895, and their partnership became one of the most productive collaborations in scientific history. Working in a converted shed with inadequate equipment, they began investigating the strange radiation emitted by uranium compounds, a phenomenon that had recently been discovered by Henri Becquerel. Marie Curie coined the term radioactivity to describe this emission of energy, and she hypothesized that it came not from molecular interactions, but from the atom itself. A radical idea at a time when atoms were thought to be indivisible and unchanging. The Curie's work was painstaking and physically demanding. To isolate the radioactive elements they suspected were present in uranium ore, Marie processed tons of pitchblende, a mineral ore, in large pots, stirring, boiling, precipitating, trying to concentrate whatever was causing the radiation. It took years of this exhausting work, but in 1898 they announced the discovery of two new elements: polonium, named for Marie's homeland of Poland, and radium, from the Latin word for ray. The work was dangerous, though they didn't fully understand the dangers at the time. They handled radioactive materials without protection, and Marie carried test tubes of radium in her pockets, charmed by the way they glowed in the dark. In 1903, Marie, Pierre, and Henri Becquerel were awarded the Nobel Prize in Physics for their work on radioactivity. Marie Curie became the first woman to win a Nobel Prize, though initially the committee had planned to honor only Pierre and Becquerel. Pierre insisted that Marie's contributions were at least equal to his own, that without her insight and determination, the work would not have been possible. In 1906, tragedy struck when Pierre was killed in a street accident in Paris. Marie, grief-stricken, continued her work. She succeeded him as professor at the Sorbonne, becoming the first woman to teach there. In 1911, she was awarded a second Nobel Prize, this time in chemistry, for her discovery and isolation of radium and her studies of its properties. She is still the only person to have won Nobel Prizes in two different sciences. During World War I, Curie developed mobile X-ray units, called Petites Curies, which she and her daughter Irene drove to the front lines to help doctors locate bullets and shrapnel in wounded soldiers. After the war, she continued her research and worked to establish the Radium Institute in Paris, which would become a leading center for research in radioactivity. She trained women scientists, encouraged their work, and advocated for international cooperation in science. Marie Curie died in 1930 from aplastic anemia, almost certainly caused by her prolonged exposure to radiation. Her papers, even her cookbook, are still radioactive and are stored in lead-lined boxes. Her life was one of extraordinary achievement, but also of determination in the face of both scientific challenges and pervasive sexism. Even after winning 2 Nobel Prizes, she faced criticism and obstacles because she was a woman. But she persisted, and her legacy is immeasurable, not just in her scientific discoveries, but in proving beyond doubt that women belonged in science, that they could achieve at the highest levels, that genius has no gender. While Marie Curie was becoming famous, another brilliant physicist was working in Germany, making discoveries that would change the world but would receive far less recognition than she deserved. Lise Meitner was born in Vienna in 1878, and from an early age showed exceptional mathematical ability. She earned a doctorate in physics in 1906, becoming only the second woman to earn a doctorate from the University of Vienna. She moved to Berlin to continue her research, where she began collaborating with chemist Otto Hahn. For more than 30 years, Meitner and Hahn worked together, studying radioactivity, discovering new isotopes, and pushing the boundaries of nuclear physics. Meitner was not just Hahn's assistant, but an equal partner, bringing theoretical insights to complement his experimental skills. But as the 1930s progressed and the Nazis rose to power in Germany, Meitner, who was of Jewish descent, found herself in increasing danger. In 1938, with Germany's annexation of Austria making her Austrian citizenship worthless, she was forced to flee Germany with almost nothing, escaping to Sweden with the help of colleagues who smuggled her across the border. Even in exile, she continued to work. And when Hahn wrote to her about strange experimental results he had obtained in splitting uranium atoms, Meitner realized what he had done but didn't fully understand. She recognized that the uranium nucleus was undergoing fission, splitting into smaller atoms and releasing tremendous energy. She and her nephew, physicist Otto Frisch, worked out the theoretical basis for nuclear fission and published their findings. This discovery became the foundation for both nuclear power and nuclear weapons. In 1944, Otto Hahn was awarded the Nobel Prize in Chemistry for the discovery of nuclear fission. Lise Meitner was not included, despite her crucial contributions to the work and her explanation of the theoretical basis for what Hahn had observed. She was nominated for the Nobel Prize numerous times but never won. The omission is now widely recognized as one of the most egregious examples of a woman scientist being denied recognition for her work. Element 19 Meitnerium is named in her honor, and over time, historians and scientists have worked to ensure that her contributions are acknowledged. She lived to age 89, dying in 1968, always maintaining her dignity and her love for physics, even as she acknowledged the injustice of how she had been treated. In the early 20th century, mathematics was undergoing revolutionary changes, and at the center of many of those changes was Emmy Noether, a German mathematician born in 1882. Despite her obvious talent, she faced enormous obstacles. Women were not officially allowed to study at German universities, so she had to audit classes unofficially. Eventually, she earned a PhD in 1907, but even with a doctorate, no university would hire her for a paid position because she was a woman. For years, she taught unpaid at the University of Göttingen, advertising her courses under her male colleagues' names because the university wouldn't list courses taught by women. Finally, in 1919, she was given a position, though she still wasn't paid what her male colleagues earned. None of these obstacles stopped her from doing extraordinary mathematics. Her work in abstract algebra laid foundations that are still fundamental to the field, but perhaps her most famous contribution is Noether's theorem, which proved a deep connection between symmetries in physical systems and conservation laws. In simpler terms, she showed that the fundamental laws of physics, like conservation of energy and momentum, arise from underlying symmetries in nature. This theorem became central to modern physics, from quantum mechanics to relativity. Albert Einstein wrote of her, "In the judgment of the most competent living mathematicians, Fraulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." When the Nazis came to power, Noether, who was Jewish, was dismissed from her position. She fled to America, where she taught at Bryn Mawr College and the Institute for Advanced Study in Princeton. She died suddenly in 1935 from complications following surgery at the age of 53. The mathematical community mourned the loss of one of the most brilliant minds of the century. In the early 20th century, in Hawaii, a young black chemist named Alice Ball was making a breakthrough that would change the treatment of a devastating disease. Born in 1892, Ball showed an early aptitude for chemistry, earning 2 bachelor's degrees by the time she was 20, one in pharmaceutical chemistry and one in pharmacy. In 1910, at the age of 23, she became the first woman and the first African American to earn a master's degree from the University of Hawaii, where she researched the properties of the chalmuogra tree. For centuries, oil from this tree had been used as a topical treatment for leprosy, a disease that caused severe skin lesions and nerve damage and led to significant social stigma. But the oil was thick and difficult to inject, and oral consumption caused nausea. Ball developed a technique to modify the oil's chemical structure, creating an injectable form that was effective in treating leprosy. The Ball method became the most effective treatment for leprosy until synthetic drugs were developed in the 90s, and it gave hope to thousands of people who had been isolated in leprosariums. Tragically, Ball died in 1916 at the age of just 24, likely from complications following a laboratory accident where she inhaled toxic gas. After her death, another chemist continued her work but published the findings without crediting her. For decades, her contribution was forgotten. It wasn't until the late 20th century that historians rediscovered her work and began giving her the recognition she deserved. The University of Hawaii now awards the Alice Ball Scholarship, and her story reminds us how many contributions by women, especially women of color, were erased or forgotten, their work stolen or attributed to others. The middle of the 20th century brought World War II and its aftermath, a period that saw both tremendous destruction and tremendous scientific advancement. Women contributed to the war effort in numerous ways, including in scientific research that was often kept secret. After the war, as universities expanded and science became increasingly important to national priorities, more women began to establish themselves in scientific fields, though they still faced enormous challenges in gaining equal pay, recognition, and opportunities. This era brought us several women whose work would prove revolutionary, even if recognition came slowly or not at all during their lifetimes. Barbara McClintock, born in 1902, spent her career studying corn, maize, peering through microscopes at its chromosomes, making observations that were so far ahead of their time that most scientists dismissed them. She earned her PhD in botany from Cornell in 1907 and began researching the genetics of maize, developing techniques for visualizing and studying chromosomes. Through painstaking work over decades, she discovered that genes could change position on chromosomes. that genetic elements could move, jumping from one location to another. She called these jumping genes, and she proposed that they could regulate other genes, turning them on or off. This idea was revolutionary and contradicted the prevailing understanding of genetics, which held that genes were fixed in position on chromosomes. When she presented her findings in the 1940s and 1950s, the scientific community largely ignored or dismissed her work. She continued her research anyway, trusting her observations, documenting everything with meticulous care. It wasn't until the 1970s and 1980s, when molecular biology techniques allowed other scientists to confirm her findings, that her work was finally recognized as fundamentally important to understanding genetics. In 1983, at the age of 81, Barbara McClintock was awarded the Nobel Prize in Physiology or Medicine, making her the first woman to win an unshared Nobel Prize in that category. She had persisted for decades in work that others couldn't or wouldn't understand, driven by curiosity and confidence in her own observations. Her discovery of mobile genetic elements opened up entirely new areas of genetic research and has implications for understanding evolution, disease, and the fundamental nature of life itself. In England, Rosalind Franklin was using X-ray crystallography to study the structure of molecules, including coal, viruses, and most famously, DNA. Born in 1920, Franklin excelled in science from an early age and earned a PhD in physical chemistry from Cambridge in 1945. After working in Paris, where she learned X-ray diffraction techniques, she joined King's College London in 1951 to work on determining the structure of DNA. She and her student, Raymond Gosling, produced remarkably clear X-ray diffraction images of DNA, including the famous Photo 51, which showed a distinctive X-shaped pattern. These images provided crucial evidence that DNA had a helical structure. Without Franklin's knowledge or permission, this photograph was shown to James Watson and Francis Crick, who were working at Cambridge on building a model of DNA's structure. Using the data from Franklin's images, along with other information, Watson and Crick published their famous paper in 1953 describing the double helix structure of DNA. Franklin's contribution was acknowledged only briefly in their paper. She continued her research, moving on to study the structure of viruses, and publishing important work on tobacco mosaic virus and poliovirus. In 1958, at the age of 37, Rosalind Franklin died from ovarian cancer, likely caused by exposure to radiation during her years of working with X-ray equipment. 4 years later, in 1962, Watson, Crick, and Maurice Wilkins, who had worked in the same laboratory as Franklin, were awarded the Nobel Prize for the discovery of DNA's structure. Nobel Prizes are not awarded posthumously, so Franklin could not be honored. But even if she had lived, it's uncertain whether she would have been included, given how her contribution was downplayed during her lifetime. In the decades since, as the full extent of her work has become clear through her published papers and laboratory notebooks, scientists and historians have worked to ensure that Rosalind Franklin receives proper credit as a crucial contributor to one of the most important discoveries in biology. Dorothy Crowfoot Hodgkin was also using X-ray crystallography, but her focus was on determining the structures of biochemically important molecules. Born in 1910, she studied chemistry at Oxford, then did her PhD at Cambridge, where she learned X-ray crystallography from J.D. Bernal. She returned to Oxford to teach and conduct research, spending decades working on determining the structures of complex molecules. Her first major success was determining the structure of penicillin, work that was crucial during World War II when penicillin was saving lives, but its exact chemical structure was unknown. She then spent years working on vitamin B12, finally determining its structure in 1956 through complex calculations that required early computers. Her final major project was determining the structure of insulin, a project that took more than 30 years and required analyzing hundreds of thousands of reflections in X-ray photographs. In 1964, Dorothy Hodgkin was awarded the Nobel Prize in Chemistry for her work on determining the structures of important biochemical substances. She was only the third woman to win the Nobel Prize in Chemistry, after Marie Curie and Irene Joliot-Curie. Throughout her career, Hodgkin not only made groundbreaking discoveries, but also mentored younger scientists and advocated for international scientific cooperation and for peace. In China, then in America, Qianxiong Wu was becoming one of the world's foremost experimental physicists. Born in 1912 in China, she excelled in physics and came to the United States for graduate school, earning a PhD from Berkeley in 1940. She joined the Manhattan Project during World War II, working on the problem of radiation detection. After the war, she became a professor at Columbia University, where she conducted groundbreaking experiments in nuclear physics. In the 1950s, two theoretical physicists, Tsang-Dao Li and Chen-Ning Yang, proposed that a fundamental principle called parity conservation might not hold in weak nuclear interactions. Wu designed and conducted an intricate experiment to test this, working at extremely low temperatures to measure the decay of cobalt-60 atoms. Her experiment showed that parity was indeed violated, that nature does have a preferred handedness at the quantum level. This was a revolutionary discovery that changed fundamental understanding in physics. In 1957, Li and Yang were awarded the Nobel Prize in Physics for their theoretical work. Wu, whose experimental work had been essential in proving the theory correct, was not included in the prize. The omission was widely criticized, and Wu continued to receive many other honors, but the Nobel Prize remained out of reach. She continued her research for decades, making important contributions to experimental physics, and she became a strong advocate for women in science, speaking openly about the discrimination women faced and encouraging young women to pursue scientific careers. Rachel Carson, born in 1907, trained as a marine biologist at a time when few women entered that field. She earned a master's degree in zoology from Johns Hopkins University and worked for the U.S. Fish and Wildlife Service, writing pamphlets and articles about marine life. But she was also a gifted writer, and in her spare time she wrote books that brought the wonder of the ocean to general readers. Her book, The Sea Around Us, published in 1951, became a bestseller and established her as a prominent science writer. But it was her final book, Silent Spring, published in 1962, that would make her one of the most influential figures in 20th century science and environmental policy. Silent Spring documented the harmful effects of pesticides, particularly DDT, on the environment and on human health. Carson showed how pesticides were accumulating in the food chain, killing not just pests but also birds and other wildlife, contaminating soil and water, and potentially harming people. The book was meticulously researched, drawing on hundreds of scientific studies, yet it was written in accessible, powerful prose that ordinary readers could understand. The chemical industry attacked Carson viciously, trying to discredit her work and her personally, calling her hysterical and unqualified, even though her science was sound and her documentation thorough. But the public believed her, and Silent Spring sparked a massive environmental movement. It led directly to the creation of the Environmental Protection Agency, to bans on DDT and other dangerous pesticides, and to a fundamental shift in how people thought about humanity's relationship with the natural world. Carson died in 1964, just 2 years after Silent Spring was published, from complications of breast cancer. But her work lived on, changing policy, changing consciousness, demonstrating the power of a scientist who could not only conduct research, but also communicate its importance to the world. As we move through the 1960s and into the decades beyond, we encounter women scientists who benefited from the doors that earlier women had begun to open, but who still faced significant obstacles and who made contributions that reshaped entire fields. This period also saw the beginning of more explicit advocacy for women's rights in science, as women began to organize, to demand equal treatment, to refuse to be silent about discrimination. And yet, even as some progress was made, many women scientists remained invisible, their contributions unrecognized or attributed to others, particularly women of color, who faced intersecting forms of discrimination. At NASA's Langley Research Center in Virginia, during the 1940s, 1950s, and 1960s, a group of African American women mathematicians were performing calculations crucial to America's aeronautics programs and, eventually, to the space race. They worked in the West Area Computing Section, a segregated group that performed complex mathematical calculations for engineers. These women were human computers, doing by hand the calculations that would later be performed by electronic computers. 3 of these women, Katherine Johnson, Dorothy Vaughan, and Mary Jackson, would eventually become somewhat famous through the book and movie Hidden Figures. But for decades, their work and the work of dozens of their colleagues went largely unrecognized outside of NASA itself. Katherine Johnson was born in 1918 in West Virginia. From an early age, she displayed extraordinary mathematical ability, graduating from high school at 14 and from college at 18. She became a teacher. But in 1953, when she learned that NASA's predecessor, NASA, was hiring Black women, mathematicians, she applied and was accepted. She began working in the segregated West Area Computing Section, but was quickly reassigned to other groups because her skills were exceptional. She calculated trajectories for America's first manned space flights, including Alan Shepard's 1961 flight and John Glenn's orbital flight in 1962. When NASA began using electronic computers for these calculations, Glenn specifically requested that Johnson verify the computer's numbers before he would agree to fly. "Get the girl to check the numbers," he said. If she said they were good, he would trust them. Johnson also performed trajectory analysis for the Apollo program, including the Apollo 11 mission that landed the first humans on the Moon, and for the Space Shuttle program. She worked at NASA for 33 years, authoring or co-authoring 26 research reports. Despite her crucial contributions, she faced both racial and gender discrimination throughout her career, working in segregated facilities, being denied opportunities for advancement, and receiving less recognition than her white male colleagues doing comparable work. It wasn't until late in her life, particularly after the publication of Hidden Figures in 2016, that she received widespread recognition. In 2015, President Obama awarded her the Presidential Medal of Freedom. And in 2019, NASA named a building at Langley in her honor. Katherine Johnson died in 2020 at the age of 101, having lived long enough to see her contributions finally acknowledged. Dorothy Vaughan was born in 1910 and was working as a math teacher when she was recruited to work at Langley in 1943 during World War II. She joined the West Area Computing Section and in 1949 became its supervisor, making her the first black supervisor at NACA and one of very few female supervisors in the organization. She led the West Computing Group for years, ensuring high-quality work from her team. When NASA introduced electronic computers, Vaughan recognized that human computers would soon become obsolete. She taught herself Fortran, one of the early programming languages, and then taught it to her staff, ensuring that they would remain valuable even as their roles changed. She became an expert programmer and worked on numerous projects during the space program. She retired from NASA in 1971. Like Johnson, Vaughan's contributions were not widely known until the publication of Hidden Figures. She died in 2008, less than a decade before the world would learn her story. Mary Jackson was born in 1921 in Hampton, Virginia. She earned degrees in mathematics and physical sciences from Hampton Institute and worked as a teacher and in other positions before joining NACA in 1951. She started as a human computer but aspired to become an engineer. To do so, she needed to take graduate-level courses that were offered at a whites-only high school. She petitioned the city of Hampton for permission to attend, and her petition was granted. After completing the necessary courses, she became NASA's first black female engineer in 1958. She worked in aeronautics, conducting wind tunnel experiments and studying airflow around aircraft. But despite her qualifications and achievements, she found it difficult to advance to management positions. In 1979, she left engineering and took a position in NASA's Equal Opportunity Office, where she worked to improve hiring and promotion of women and minorities at NASA. She believed she could have more impact by helping other women and people of color advance than by continuing her own engineering career. Jackson died in 2005. In 2020, NASA renamed its headquarters building in Washington, D.C., the Mary Jackson NASA Headquarters Building in her honor. These three women, and dozens of their colleagues whose names are less well known, were essential to America's success in aeronautics and space exploration. They worked with extraordinary skill and dedication, often in difficult conditions, performing calculations that engineers depended on, making discoveries and contributions that were crucial to keeping astronauts safe and missions successful. Their story reminds us that for every famous scientist whose name we know, there are many others who contributed just as significantly, but whose work was done in shadows, unrecognized because of their race, their gender, or both. In 1983, another barrier fell when Sally Ride became the first American woman in space. Born in 1951, Ride earned a PhD in physics from Stanford and joined NASA's astronaut program in 1978. On June 18, 1983, she flew aboard the Space Shuttle Challenger, operating the shuttle's robotic arm to deploy satellites. Her flight captured national attention and inspired countless young women to consider careers in science and engineering. Ride flew in space twice and, after leaving NASA, became a physics professor and devoted herself to encouraging young people, especially girls, to study science. She founded Sally Ride Science, an organization dedicated to supporting students interested in STEM fields. She died in 2012 from pancreatic cancer, but her legacy continues, a symbol of what women can achieve when given the opportunity. In astronomy, Vera Rubin was making observations that would reshape our understanding of the universe. Born in 1928, she became interested in astronomy as a child, watching stars from her window. She earned her PhD in astronomy in 1954 and spent her career studying the motion of galaxies. Working with her colleague Kent Ford, she measured the rotation rates of spiral galaxies and made a puzzling discovery. The stars at the outer edges of galaxies were moving just as fast as stars near the center, which didn't make sense according to the laws of gravity as applied to the visible matter in those galaxies. The only explanation that fit the data was that galaxies contained far more matter than could be seen, invisible matter that exerted gravitational force. This invisible matter came to be called dark matter, and Rubin's work provided some of the strongest evidence for its existence. Dark matter now is understood to make up most of the matter in the universe, yet we still don't know what it is. Rubin's discovery was one of the most important in 20th century astronomy, yet she never received a Nobel Prize, an omission that many in the scientific community considered unjust. She was, however, awarded numerous other honors and spent her career advocating for women in astronomy, mentoring younger scientists, and speaking out about gender discrimination in science. She died in 2016, still wondering about the nature of the dark matter she had helped discover. In primatology, Jane Goodall was revolutionizing how we study animal behavior. Born in 1934 in England, Goodall had loved animals since childhood. Without a university degree initially, she traveled to Kenya and met the paleontologist Louis Leakey, who hired her as his secretary and then gave her an opportunity that would change science. He sent her to Tanzania in 1960 to study wild chimpanzees, believing that a patient observer without formal training might notice things that trained scientists, with their preconceptions, might miss. Goodall spent months gaining the trust of chimpanzees in Gombe Stream National Park, and her observations overturned fundamental assumptions about primate behavior and about what makes humans unique. She observed chimpanzees making and using tools, something that had been thought to be uniquely human. She documented complex social behaviors, hunting, warfare between groups, compassion, and adoption. Her approach, which involved getting to know individual chimpanzees, giving them names, and documenting their personalities and relationships, was initially criticized by some scientists as too subjective, but her careful documentation and the depth of her insights eventually won widespread respect. She did earn a PhD from Cambridge, one of the few people to do so without first having earned a bachelor's degree. Goodall's work not only advanced primatology, but also changed how humans think about our place in the natural world. She has spent the latter part of her career advocating for conservation and animal welfare, traveling constantly to speak about environmental issues. At 91, she continues her work, a living testament to the power of patience, observation, and respect for the natural world. In medicine, Mae Jemison became the first African-American woman to travel to space. Born in 1956 in Alabama, Jemison earned degrees in chemical engineering and African-American studies from Stanford, then earned her MD from Cornell Medical College. She worked as a doctor with the Peace Corps in West Africa before applying to NASA's astronaut program. She was accepted in 1987 and flew aboard Space Shuttle Endeavour in 92, serving as a mission specialist conducting experiments on weightlessness and motion sickness. After leaving NASA, Jemison founded several companies working on technology applications in developing countries and established programs to encourage young people, especially minorities, to pursue science and technology. She has taught at several universities and continues to work at the intersection of science, technology, and social issues, embodying the idea that science should serve humanity. In the late 20th and early 1st centuries, women scientists continued to make groundbreaking discoveries across all fields of science, and slowly, very slowly, recognition began to come more regularly, though equality remains elusive. These recent decades have brought us women who have won Nobel Prizes, revolutionized medicine, changed how we think about editing genes, discovered life-saving treatments, and expanded our understanding of everything from the smallest particles to the largest structures in the universe. In China, Tu Youyou turned to traditional Chinese medicine texts to find a treatment for malaria. Born in 1930, Tu studied pharmacology and joined China's Academy of Traditional Chinese Medicine. During the Vietnam War, as malaria was killing soldiers on both sides, China launched a secret project to find new anti-malarial drugs. Tu led a research group that screened over 2,000 traditional Chinese remedies. In ancient texts, she found references to sweet wormwood being used to treat intermittent fevers. She extracted a compound from the plant, artemisinin, which proved remarkably effective against malaria parasites. Artemisinin-based therapies have since saved millions of lives, particularly in developing countries where malaria remains a major killer. In 2015, Tu Youyou was awarded the Nobel Prize in Physiology or Medicine, becoming the first Chinese scientist to win a Nobel Prize in a scientific category, and the first Chinese woman to win a Nobel Prize in any category. She was in her 80s when she received the prize, recognition that came after decades of work that had already transformed public health across the globe. In molecular biology, Jennifer Doudna was part of the team that developed CRISPR-Cas9, a revolutionary gene editing technology. Born in 1964, Doudna earned her PhD in biological chemistry and molecular pharmacology from Harvard. She became interested in RNA, the molecule that carries genetic information and performs various functions in cells. Working with Emmanuel Charpentier, a French microbiologist, Doudna figured out how a bacterial immune system could be adapted into a precise tool for editing DNA. CRISPR allows scientists to target specific genes and alter them, potentially correcting genetic diseases, creating drought-resistant crops, and enabling countless other applications. The technology is so powerful and so accessible that it has raised ethical questions about how it should be used, particularly regarding editing human embryos. In 2020, Doudna and Charpentier were awarded the Nobel Prize in Chemistry for developing CRISPR-Cas9. The prize came just 8 years after their initial publication, unusually fast for a Nobel Prize, reflecting how revolutionary and important the technology is recognized to be. Doudna has been active in public discussions about the ethics of gene editing, arguing for responsible use while acknowledging the technology's enormous potential to reduce suffering. Francis Arnold pioneered a technique called directed evolution for creating new enzymes. Born in 1956, Arnold earned her PhD in chemical engineering from Berkeley and became a professor at Caltech. She recognized that evolution, the process that has shaped all life on Earth, could be harnessed in the laboratory to create new proteins with useful properties. By introducing mutations into genes, selecting for desired traits, and repeating the process over many generations, she could evolve enzymes that performed functions that nature had never developed. Her techniques have led to new catalysts for making pharmaceuticals, biofuels, and other chemicals in more environmentally friendly ways. In 2018, Frances Arnold was awarded the Nobel Prize in Chemistry, becoming only the 5th woman to win that prize. She has been an advocate for diversity in science and for sustainable chemistry, using biological processes instead of harsh industrial methods. The stories continue. Women scientists working now in laboratories and field stations and at computers around the world, making discoveries, solving problems, asking new questions. They work in every field of science imaginable, from astrophysics to zoology, from computer science to marine biology. Some will be recognized with prizes and honors. Many will not. But all are part of the continuing story of human curiosity and the drive to understand our world. As you lie here tonight, drifting toward sleep, consider the long arc of this story. From ancient physicians working when history itself was young, through centuries when women had to fight for every opportunity to learn and contribute, through eras when their work was stolen or dismissed, to the present day where progress has been made but equality remains a work in progress. Think about Marie Curie, working in a cold shed, stirring vats of pitchblende, driven by curiosity about the invisible forces emanating from certain elements. Think about Rosalind Franklin, peering at X-ray photographs, seeing patterns that revealed the structure of life itself, even as others would take credit. Think about Katherine Johnson, calculating trajectories by hand. Her work so trusted that astronauts wouldn't fly without her verification. Think about Barbara McClintock, alone in a cornfield, observing patterns in maize chromosomes that everyone told her couldn't exist, trusting her eyes and her mind even when others dismissed her. Think about Rachel Carson, writing late into the night, documenting the silent spring knowing the chemical industry would attack her, but writing anyway because the truth mattered more than comfort. These women, and thousands of others whose names you'll never know, looked at the world and asked questions. They refused to accept that their gender should limit their curiosity or their contributions. They worked in difficult conditions, often without support, frequently without recognition, sometimes having their work stolen or attributed to others. They persisted anyway, driven by something deeper than the desire for fame, driven by the need to understand, to discover, to know. Their legacy is not just in the discoveries they made, though those are considerable. Their legacy is in the proof they provided that science is for everyone, that insight and intelligence are not bounded by gender, that excluding half of humanity from scientific endeavor means losing half of humanity's potential to understand and improve the world. You are connected to these women, to their struggles and their triumphs. The medical treatments you receive, the technologies you use, the food you eat, the understanding of the world you carry with you, all of these bear the marks of women's contributions to science, often invisible contributions, often unrecognized, but real nonetheless. The world these women helped build and understand is the world you live in. The questions they asked opened pathways for more questions. The barriers they broke down, though not entirely dismantled, at least have cracks now, spaces where more women can slip through, can claim their place in the great human project of understanding the universe. As you drift toward sleep, you might think about the young girls and women right now, in laboratories and classrooms around the world, who are the next generation of scientists. They stand on the shoulders of all those who came before, carrying forward questions old and new, applying new tools to ancient mysteries, dreaming of discoveries that will reshape what we know. Some will face obstacles. Many will encounter skepticism or discrimination. But they persist, inspired by the long line of women who refused to be silenced, who refused to accept that science was not for them, who looked at the stars and the cells and the mathematical patterns and said, "I want to understand, and I will not be stopped." The history of women in science is not a side story. It is not a separate narrative running parallel to the main thread. It is woven throughout the entire history of human knowledge, present at every turn, essential to every discovery, even when it was invisible, even when it was erased. Recognizing this, honoring it, learning these names and these stories is not just about fairness or inclusion, though those matter enormously. It is about understanding the true history of how humans came to know what we know, about acknowledging all the minds and hand and voices that contributed. It is about seeing clearly, without the distortions of bias and erasure, the full scope of human achievement. If you're still awake, feeling the pull of sleep, but not quite ready to surrender to it, let yourself rest in this knowledge. The work continues. The questions multiply. The discoveries await. And somewhere in the world, right now, a woman is looking through a microscope, or solving an equation, or analyzing data, or observing the natural world, and she is adding to the great edifice of human knowledge, building on the foundation that those before her laid, preparing the ground for those who will come after. Sleep well, knowing that the universe is vast and mysterious, and that humans, in all our diversity, continue to reach out to understand it, continue to ask why and how, continue to discover and create and illuminate the darkness. If these stories have given you something to think about as you rest, if they have reminded you that history is richer and more complex than we often remember, consider liking this video and subscribing to the channel. It helps others find these stories, helps more people discover the remarkable women who shaped science and our world. Good night. May you dream of discovery, of persistence, of women who looked at the impossible and made it possible, of minds that refused to be limited, of questions that opened worlds. Rest well. Tomorrow, those questions continue, and new ones emerge, and the great work goes on.